Ethernet is currently the dominant wired LAN technology. Other technologies like FTDI, ATM, and token ring, which were successful for a few years, could not gain the success Ethernet has gained in this domain. Being the first technology, being able to keep up with the ever-increasing data rates, and the simplicity of this protocol could be seen as the reasons contributing to its success. Historically, different topologies have been adopted in implementing LANs using Ethernet. The early bus topology, which was popular from 70s to mid-90s, was replaced with the more successful hub-based star topology. In the early star topology, a hub was a physical broadcast at the center, connected to all of the devices which were called spokes. In this topology, the hub is simply a physical layer repeater that amplified and sent out the bits on all its ports once received on one of the inputs. The slightly modified star topology is the prevailing technology today. In bus topology, all nodes share one bus, and therefore they share the collision domain. This means that their transmissions could collide. In the star topology, the hub, or active switch, is in the center. Over time, in the change to newer technologies, the hub, which was a physical layer repeater, was replaced with a layer 2 switch. Therefore, each spoke runs a separate Ethernet protocol, and the switch is a layer 2 store and forward device. We will discuss switch in a little bit further detail later in this module. We discussed that in layer 2, the sending adapter encapsulates the IP datagram within a frame. Let's take a look at Ethernet frame structure. An Ethernet frame starts with 8 bytes called preamble. The first 7 bytes of the preamble have the bit pattern 10101010, and the last byte has the pattern 10101011. These 2 last bits are letting the adapter know that the important fields of the frame are now coming. You may wonder why this preamble is used. It is used to absorb the drift of the clocks while the 2 adapters on the 2 sides are trying to synchronize their clocks to start communicating. The next fields are the destination and source MAC addresses. If an adapter receives a frame with matching destination MAC address or with broadcast MAC address, as we saw in the ARP protocol, it passes the data within the frame to network layer protocol. Type, which is the next field, indicates the higher layer protocol. The network layer protocol is usually IP, but note that it can be other network layer protocols like AppleTalk. This is set in the type field of the Ethernet frame using a number that indicates the used protocol in the network layer. Type field is 2 bytes. Next is the data or payload. This is the field that contains the IP datagram or the alternative network layer datagram. This can vary between 46 to 1,500 bytes, as the Ethernet maximum transmission unit, or MTU, is 1,500 bytes. This means if the IP datagram is less than 46 bytes, this field needs to be stuffed up to 46 bytes. And if it is more than 1,500 bytes, it needs to be fragmented. The length of the IP datagram will be used in the network layer to reassemble the fragmented frames or separate the small frames from the stuffed bits. And last but not the least, 4 bytes of cyclic redundancy check, or CRC, is used in the Ethernet frame to check the correctness of the frame at the receiver. Ethernet provides a layer 2 connectionless service. This means there is no handshaking or connection establishment between the sending and receiving NICs before sending the Ethernet frame. The Ethernet service is also unreliable. The receiving NIC does not send ACKs or NACKs to sending NIC. If the CRC check of the frame fails, it simply discards the frame. If higher layer reliable data transfer is used, the contents missed due to dropped frames could be resent using upper layer mechanisms. Otherwise, the data within the dropped frame is lost. Ethernet uses CSMA-CD with binary backoff that we previously discussed. Ethernet is not a single protocol standard. There are many different Ethernet standards that are a combination of link and physical layer standards. In these protocols, MAC protocol and frame format is supported over different speeds and different physical layer media formats. For example, 100 base T4 for copper and 100 base FX for fiber. The first part, for example, 100, as we see in the figure, refers to the speed of the standard. For example, here it is 100 megabit per second. Base refers to baseband Ethernet, meaning the media carries Ethernet frames. And the last part of the acronym refers to the physical media. For example, T for twisted copper wire and F for fiber.